It's great to see so many familiar faces, so much support. I'd start off with saying thanks to Basti, my advisor, and to my committee members, their support, and Jeff, who is on Zoom with us. Um, so today I will be talking about my thesis on autonomous robotic data gathering and how we can improve these robotic systems to increase their effectiveness in real-world applications. So gathering information about our physical world can play a crucial role in many different applications and can take many different forms. So here we see a couple different examples of robots as well as applications that this work spans. And they have many different applications such as like inspections or disaster relief or scientific research. And in these applications currently, in a lot of them, we have humans filling these roles, but that can sometimes be dangerous, can be slow or tedious, and can be error prone. And so using a robot to gather data has many benefits. One of them being that it frees up the operator to make higher level decisions. It allows them to be farther away from sources of danger, such as like fire or radiation, or risk of, let's say, a building collapsing. And these robots can often reach areas that we cannot ourselves, such as other worlds. And this robot can also leverage outside levers that allow it to make optimal choices, and it can make decisions sometimes faster than a human can. And then these benefits in turn create hopefully a system that you can ideally deploy quickly and also allows us to scale the impact by being able to also scale the number of robots. But why is information gathering or data gathering hard? So in the real world, when a robot is deployed, there are often many different disturbances that come about, whether it be at ocean currents or winds. And planning these paths in these high dimensional spaces with sensor constraints and motion constraints can be challenging and is often most times an NP-hard problem. And it's hard to make these systems extremely reliable, adaptable, with little or no human input. One of the other challenges is being able to estimate the value of a future action or a future observation and modeling this world belief that you have. And often many common approaches may oversimplify or approximate the solution, leading to suboptimal results. So the goal of this work is to help enable autonomous data gathering to match and hopefully even exceed that of human performance. And we will do this by developing intelligent systems that consider the challenges of the real world and what gaps still exist. So in my thesis, I focus on three areas where I believe autonomous information gathering can be improved by integrating long horizon reasoning, environment dynamics, and also enhanced world belief models. So the outline of my thesis in my presentation follows these three areas of improvement. So first, I will focus on informative path planning for information gathering. I will explain how we can reason over long horizons, creating adaptive and efficient algorithms that can run on board a vehicle or UAV. Then I'll explain how we can incorporate the impact of wind on drones specifically, both in planning the paths as well as assessing the risk of executing a path. And then lastly, I'll describe how we can use prior data to better inform future robot decision-making to more accurately estimate the value of the future action. So let's begin with informative path planning, what it is, and our work within this space. So first, let's take a step back and look at just path planning in general, and the different objectives that you may have for a robot when planning a path. So first, we're going to look at goal-oriented path planning. So let's say we have a drone with a start state, and then a final state that you want to get to. And then let's say there are a couple obstacles in the space. And maybe you want, in this case, the objective of the shortest path. Maybe your path looks something like this, right? And it skirts really close to this obstacle and gets to the final state. Maybe you may have a fastest path that may look different. Maybe it's a smooth path that goes around. But then you may say, well, maybe we want a safest path. In this case, maybe it's a more jagged, slow path, but it stays really far away from these obstacles. And then maybe you would want an energy efficient path. Maybe this looks different in this case, where it follows some sort of wind field and goes a long way around. So now we can shift gears a little bit and look at a different type of path planning problem where we don't have a goal state, and the objective is more, I guess, nuanced. One of these could be something like a full coverage path. Now it looks something like this, where you want to cover all the space and be able to observe all of it fully. However, you may think, well, our drone doesn't really have that much battery, and so we need to implement some sort of constraint on the budget or the amount of battery that it has. And so maybe that only allows you to see a part of the space. However, there may be in your application certain areas of this map that you care more about, such as if you were wanting to inspect around these obstacles, let's say there were some sort of like tank that may be leaking or something. And in this case, that introduces what we call a informative path. which is where we're trying to maximize some sort of objective function that measures information gain while still respecting this budget constraint. And maybe in this case, it looks something like that. So many robotic applications can be framed as this informative path planning problem. For instance, in this scenario, we have our drone, which is autonomously and efficiently mapping where the cars are within this defined space. And this planning task is very challenging. It's planning in 3D space. It has to figure out what altitude it should fly at. It needs to know where it should go within that limited amount of battery life that it has. It needs to also think about how does it update its world belief model given a specific observation, given that it knows the accuracy of its car detector model. So we're going to formalize this a little bit and go through what is the informative path finding problem. So here's the objective function that we have. So first we have our trajectory tau. We have a set of possible trajectories which respect the motion constraints of our system. We have a cost. This cost could be a distance or amount of battery expended or time. Then we have this budget, which is correlated with that cost, which we need to stay below. Then we have some objective function, which could be some information gain metric that we're trying to maximize. And then we also have a sensor model that we use to understand how our belief changes given observations. And then we have our world belief model, which models our understanding of the world around us, that information that we're gathering and how that affects that. So what are these specific challenges within informative path planning? So one of them is the motion constraints, which can be challenging, especially with things such as like a fixed wing drone, or if we want to have really smooth paths. We also need to be planning over long horizons, which is challenging. We need to take into account these budget constraints. And then we need to be able to estimate the utility or the benefit of a specific action to our model. And then we want this planner to be online and adaptive. So as the world changes around it, it needs to change its plan. So there are three of our categories that we can essentially categorize these different approaches to informative path planning. So one of those is through discretized graph-based approaches. And there are a lot of great ones out there that are often resolution complete, but they can struggle with having a large number of nodes. And due to this discretization of the space, sometimes for applications, it can lead to oversimplifications, and most don't allow for revisiting specific nodes based on the formulation. Another approach could be a receding horizon approach. And these are often real-time and are locally optimal. However, they're not leveraging the entire understanding of the space, and they can get stuck in local minima sometimes. And then another one is sampling-based approaches. These work well in high-dimensional spaces. They are often asymptotically optimal at any time. However, sometimes they can still struggle in large search spaces. So in our work, we introduced what we call IA Tigris, which is an incremental and adaptive sampling-based planner for online information planning or informative path planning. And this planner is a global path planner, meaning it's planning over the entire budget. It works in large scale with large budgets and long horizons. It works with continuous search spaces with different types of motion constraints that are realistic to the vehicles we use. It's efficient. It's able to compute these paths on board, and it's both adaptive and incremental. So first, what is sampling-based planning? So within sampling-based planning, we're creating a tree of potential trajectories by iteratively sampling in the space and connecting those states, respecting the motion model. And then we continue to expand this tree. And over time, when the planning time is expended, we then select the path that is the best within that set. And some of the benefits of this is it works well in these high-dimensional spaces and works with complex motion models because you're just having to connect two states within this tree. But though it's efficient, in our cases with these large search spaces, we want to be able to focus this tree that we're creating within areas of high potential for information gain. Especially in some large spaces, we may have big pockets of no information that we need to gather. So one of the contributions of our work is how to approach this through informed sampling. What this means is rather than uniformly sampling within the space, we do a weighted sample that correlates with the amount of expected information gain that we will get. And the way we do that is first sample within the information map that we have. And after we have that state, we then uniformly sample within the states that would observe that space. And then that creates a more nuanced distribution, which we can see an example here. So on the top, we had informed sampling. The colors of this belief space, the more pink colors in this projector, are areas where we would expect more information gain. And then on the bottom, we see a uniform sample. In this case, this yields higher quality paths. So how do we measure what is an informative path? What does that mean? So in implementation for this work, we represent our belief space as a grid where each cell identifies or classifies if there's an object of interest or not within it. And so every time we get a measurement, whether it be positive or negative, we update our belief using a Bayesian update. And then to quantify the reward, we use a reduction in entropy, or essentially reduction in the uncertainty of that map in our belief space. And then also in our work, rather than quantifying the reward for a path as just that sample point or that sampled state, because most of our systems are continuously gathering information, we calculate that information gain for the entire trajectory, which gives us a better estimate of the information gain as we execute a future path. And so as mentioned before, one of the challenges of making our planner is we want it to be adaptive to new information and replan on the fly. So a simple way you could make something adaptive is just to replan every certain period of time. However, this is computationally expensive, and you're often throwing away past search efforts. So the key idea is finding where we can reuse past planning efforts, and rather than discarding it, is you update it and then continue to refine. And we do this through incremental planning, where we build, update, and refine our solutions over time. So what does this look like? So let's say that we have our start position of our robot, and we plan this tree. We select the best one, and we start to execute that path. As we start to execute it, we trim off the parts of the tree that are no longer relevant in this case, and then we update our current tree based on the belief map and our remaining budget, and then we continue to expand from that remaining tree. And this saves a lot of time. And one of the novel things we introduced in our paper was a way of embedding our belief space in a memory and computationally efficient way within each node. That allows us to recycle this tree where before would take maybe like 2 seconds for these large trees. It's now down to a couple milliseconds. And we tested our method on a hex rotor where we're trying to map the location of cars in the space. Here you see a visualization of a prior where the color represents uncertainty, and the hex rotor plans paths throughout this space to reduce that uncertainty of car locations. And so in setting up this situation for the planner, we're able to define a search boundary and any sort of prior information we have about car locations. You can do maybe the parking lot areas or specific spots we think a car might be. And then this is given to the planner as its initial belief map. And then the UAV is able to start flying over the space. In this case, it has a downward facing infrared camera that we use to detect where cars are. And that car detector can run online. And as the belief space is updating, which you'll see in a second, the planner continues to adapt and refine its plans based on what it's observing. So here we see an example of a prior. So again, we've marked essentially the parking lots where cars might be in the space. And then we also, in this case, we marked 3 spots of higher uncertainty. And then here's a resulting path that we can see from this. You can see the varying altitudes and the different spaces that it travels back and forth to these different parking lots. And one key area to look at here is you can see the spot where it doubled back around 3 or 4 times. And this is correlated to one of the spots of higher uncertainty. So we can see that it's choosing these paths that will maximize the expected information gain. So we also tested this extensively in simulations. In this case, we did it with a fixed wing drone with a forward-facing camera with a little bit of a downward pitch, similar to this image on the right. And when connecting 2 different states, rather than doing straight line connections during quad rotor, we use what's called the Dubin's path connection, which is the time optimal connection with something for a motion model that's curvature constrained. And what it consists of is full banks, straight line segments, and then full banks. And there are 4 of these different configurations, which you can see here on the bottom left. So these are called Dubin's paths. And again, for these tests, we use a grid to represent our belief space, and we update it using Bayesian updates. And then for the simulations, we randomly sampled the locations of uncertainty using Gaussians, and then ran hundreds of these tests. So here's a snapshot of what one of these may look like. So you can see the planned path in green executed in yellow. And you can see that as time goes on, that this path is further refined and changed to cover these areas of uncertainty, which are, again, the more pink color in the belief space. And then you can see that later on how it decides to instead to double back on itself in these areas of higher uncertainty rather than farther back up to the right. And then as that time goes on, you can see now that the search tree, which is in the lighter green color, no longer extends to the top right because it is running out of budget at that state. So we can see how it's adjusting to what it's seen, it's adjusting to how much time it has, and it's also over time refining that path and leading to a higher quality path rather than having a single plan, which we can see a comparison here where we have incremental and adaptive planning on the top, and then we have a static plan on the bottom where it just plans one time. And we can see how the one on the top, how its search tree, which is visualized as all the different paths, how it continues to be refined. And it's focused again in these areas of high information gain and less focused in the areas where there's no expected information gain. So compared to some baselines, we compared to a greedy method, which uses the next best action divided by the cost by the pot. We compared it to an MCTS method, which tries to balance this exploration and exploitation of different variations of paths. We also did a random one where it just chooses a random state, and then also a coverage path, which is a lawnmower path across the space. And what we found in our case, the metric that we used was a reduction in entropy. So it's a percent reduction. So 100% reduction, meaning you have no uncertainty in your map anymore. And you see in this that IA Tigris was the best performing one. Something interesting to note is in the beginning how greedy has that initial spike, which represents that it is a short horizon planner. It's myopic, and it will choose these actions that will maximize information in the next step, but not over the long run. And then we can see that also in the table, we did different budgets. And so you can see that when we did the shorter budget, the IA Tigris did beat greedy because it's optimizing over the entire budget, not over just the single next action. And then we also tested our method extensively with our sponsors with a fixed wing drone that accumulated over 20 flight hours and 100 different flights running our planner. Here's just one example. We have a black box showing the search area, and then you have a smaller black box, which is our area of higher uncertainty where there was a probability of a car being there. And you can see that the plan efficiently covered the space and did even 2 observations within that space of higher uncertainty. It was able to observe the car, localize it, and then you can see with the budget, it almost covered the entire space, the top middle map right there, that it ran on a budget essentially before it covered the entire space. And so some interesting things to note and some takeaways from IA Tigris. So we were able to demonstrate an effective information gathering in both simulation and in both in field tests for text rotors and fixed wing UAVs. We validated the impact of long horizon planning in these situations. And it also works with different motion and budget constraints. And this planner can run online. It adapts to the current information maps. However, there's one interesting thing to note here is as we look at the difference between the planned path and the executed path, you'll see that there is this deviation, right? So in this case, this is a path deviation due to wind. And it really raises that question of how do we incorporate this? Because if this is executing a different path than what we planned, our information gain will also be different than what we expected. That may not be the optimal path anymore. So how can we incorporate this wind into the path planning framework? So that leads to the next section, which really focuses on some of the challenges we face when deploying these robots in the real world. And I'll be going over the works that we have done to address incorporating wind into path planning framework for UAVs, where wind is most often something that's ignored. It's something that we just want the controller to fight and essentially offset. However, this can sometimes lead to paths that are very suboptimal, that will use more battery than we expected, and introduce the risk of running out of battery during flight. So we want to answer 3 questions, which is how can we estimate the wind field? How can we plan paths in the wind field? And then also, how can we estimate the risk of this path in the wind field? So we explored this first question in one of our works where we seek to estimate the entire wind field within an urban environment using just local measurements from a drone. And the key insight is that if you have both the angle and magnitude of the wind coming into a city, called the inlet conditions, then you can use fluid dynamics simulations to calculate the wind speed anywhere within the city. However, we don't have the inlet conditions when we go and deploy a robot, and we can't run these fluid dynamic simulations on board the drone. So our insight was to use a particle filter to solve this inverse problem of finding the inlet conditions using these local measurements. So this was our process. So on the left, you see the update loop of this particle filter. And on the right, you can see how we take these wind measurements and we use them to update the weights of this particle filter. And then we use a Gaussian process regression to use that as a surrogate model for these fluid dynamic simulations so we don't have to run them online. And then we field tested this in a urban area. It looks familiar from the first test too. And on the left, we have a 3D model that we created from this. And then there you can see the Google Maps version of it. And we placed an anemometer on the tallest building so we could gather what is the ground truth inlet conditions. And then here you can see our drone with the anemometer on top. And these are examples of some of these wind measurements that we would get as we were flying. And then this was our simple flight path that we flew. And then also visualized is the wind field as we ran it through fluid dynamics simulations using the inlet conditions of that day. And then here we have two results figures. So on the left is the wind inlet magnitude, on that right, wind inlet angle. You have the ground truth in blue. Then you have both the particle filter output and the moving average in both these reds. And you can see how it converges to the ground truth. And you can see that this is then something that we can then use to query our Gaussian process model to get the wind estimate in any part of our space. So after we've estimated this wind field, the next step is to how do we plan paths in this wind field. So as mentioned before, when we're connecting two robot states with a curvature constrained motion model, that creates what's called the Dubin's path. So we have these maximum curvature turns, and then straight line segments, and then turns. So in here. However, when we add some sort of winds, this Dubin's path is no longer the optimal path. And it can often lead to something as suboptimal or even dynamically infeasible in some cases. So one way we can solve this is using what's called a trochoidal path, which are these more spiral-like paths, which do take into account this flow field. However, you have to compute all four of these trajectories in order to find which one is optimal. And this is much, much slower than a Dubin's path calculation. In order for our global path planner to run on board and efficiently, this key connector must be extremely efficient. So in our method, we found a way to narrow down these candidate trochoidal trajectory types before having to compute them by bounding the set of possible optimal solutions and for a given conditioning and then computing the remaining ones. Our key insight was to reformulate this problem without the winds, find the bounds of the solution space, and then identify the set of candidate trajectories that contains the optimal solution. But finding this optimal path configuration when the wind is introduced is very challenging. So on the left, we see an example of no wind. This is a Dubin's path configuration. Each color represents which one is the optimal path, which set. You can see that once we introduce wind, this becomes a lot more complex. And before, where we have more defined rules, those rules no longer come into effect on the right. And so keeping all variables constant, this is even just varying the angle of the start and the goal. And you can see how much it changes the optimal solution. And then we can also see how these time optimal paths are often non-intuitive, how they can become very odd as we have high winds, and how they're very different from the Dubin's path. So how do we go about finding the optimal path configuration without having to compute all four of these? So to do this, we first have to align this x-axis of our problem with the direction of the wind. And then we can then reformulate this as a rendezvous problem by removing the winds and having this this goal point move in the opposite direction that the wind was. And then we're just essentially trying to rendezvous with that moving goal point. And so once there is no wind, we can now connect any two states using a Dubin's path connection because they're now essentially static. So as this goal point moves in the negative x direction, we divide this goal state trajectory based on when either the start or the goal heading transitions to a new quadrant, as you can see here. And this continues for all different configurations. And then all we have to do is find which of these segments that the solution lies within. And then if we know that, we know that the quadrants are constant in that space, and we can then use the Dubin's path classification rules to essentially look up what would be the set of optimal trajectories that we can then solve with the trochoidal method. And we do that by finding the traversal time from the start and the goal to one of these transition points. And when the time that it took from the start is less than the goal, we know that the solution must lie before that segment. And you can see here that we know essentially that it's in A44, meaning it's the fourth quadrant for start and goal. And we can lift up that in this case, there's only one possible optimal solution, which is a left, straight, right. So in our first results, we found that we were able to speed things up by about half the amount of time, which is pretty great. But then with a little bit more work, we're able to now, leveraging some of the properties of the problem and using Chebyshev polynomials, we're able to get that down now to 0.05 milliseconds, down from 1.7 milliseconds. If you want, you can try our work. We have it on GitHub. There's just a ROS package that you can easily implement to do these trochoidal paths as your state connector. You can also try it out on our web interface where you can mess around with it to see how this problem changes as you change the conditions. You can do things such as toggle on and off the winds and also see the set of possible solutions versus the optimal solution to get a feel for how interesting and kind of intriguing this problem is. So now we have shown how we can plan paths in wind field that are time optimal. But how do we estimate the risk of one of these paths that we're going to execute? So for this question, we focused on the energy risk of a UAV in a wind field and estimate the energy used using a learned energy model. So the main idea in this work is to leverage Monte Carlo simulations in our deep learning model that we train on hundreds of our own flights that we did. And using those different flights outputs, we were able to compute a conditional value at risk that gives you some sort of metric of how risky this path is. And so for the wind simulations, we again use computational fluid dynamic simulations, and we sample from the distribution of inlet angles from historical data from those spaces. And then we also add on a turbulence model, a Dryden turbulence model for this case. And so here you can see all the different paths. So you have these tons of tiny little lines, and the darker pink ones are the ones that use more energy. Then that creates a distribution, which we then can scale using a risk profile, which takes into account both the maximum energy your battery has, as well as essentially the tolerance of the operator and how risky they want this flight to be. And then that gives you a conditional value at risk. And so this method you could also use to evaluate something like a shipping depot, or to evaluate how much coverage you could have in a space given a specific risk profile. So from these three works, we've shown steps that we've taken to incorporate real-world disturbances into our planner, giving more optimal, feasible, and hopefully safe paths. So in the previous two sections, we focused on methods that relied on having some sort of prior of the space, some sort of map that you're planning within was structured. So in this last section, we look at the case where the robot may not have a prior, and the objective is to essentially create that space that it is going in and traversing within, and create a model of that space that it is traversing. So for this problem, we look at a task of indoor building exploration, and our objective is to gain the highest map accuracy within the least amount of time. So you have the question for this robot at all points in time, which is, where should the robot go? Reasoning over choices that will maximize its information gain. So in our planner called MapX, we approach this by using a global map predictor, which helps us reason over the value of a given action. So for example, let's say we have a ground robot here that is choosing between two different frontiers, this frontier being this boundary between known or observed space and this unobserved space. So here's very challenging, because which one do you choose? Without knowing what's in that unseen space, it's hard to create value for that action. And there are many works that use different heuristics and ways to estimate this information gain that you will get. So in our work, we leverage a map predictor. So we take in our accumulative observed map, and we pass it through an ensemble of map predictors, and that gives you a set of map predictions, which we can then take the average of and create some unified map. And then as well as we can take the variance of that to create a notion of uncertainty of our predicting model. And so now we can predict what is in this unseen space. But so now we have that question, should we just go to the space that has the highest uncertainty? Or do we need to also reason over how much we will see within that space? Or you could say the coverage or visibility at each of those frontiers. And so that was the key insight with MapX, is combining both of these, where we jointly reason over both the uncertainty of our map prediction in these unseen spaces, as well as how much we expect to see. This balances both spaces that will see well as affect the map accuracy and improve the map accuracy. So here's one example you see of just two frontiers. So we have the one on the top, which has this orange visibility mask, you can see, where it has medium uncertainty or medium coverage, but then high uncertainty, whereas the one on the bottom has really high coverage and low uncertainty. And then jointly on top of that is also farther away. So in this case, we choose the top one. It's closer, has high uncertainty, and it has pretty good coverage in this case. However, as the robot is traveling through the space, it doesn't just get observation at that frontier. It's gathering information along the entire trajectory. So similar to back in with IA Tigris, where we evaluated the value of a action as the entire trajectory, we must also estimate the information gain for an entire trajectory, not just at these frontier points at the end, but also along the entire path, and then accumulate that to essentially estimate the value of a given action. So we created one called Pipe Planner, which estimates the information gain for a frontier by using a path integration or cumulative sensor coverage paired with this map prediction. So in this work, we estimate the coverage at all points along the path and leading up to the frontier and accumulate that using both the coverage and map prediction. However, these coverage estimates at each of these points is extremely computationally expensive. So we have to leverage some things such as computational geometry and parallelization in order to really speed this up and allow this to be pretty quick. And this leads us to having state-of-the-art performance in these indoor exploration baselines. So for our tests, we use this KTH indoor floor plan data set. And we separated this into small maps, medium maps, and large maps to see the different behaviors within each of them. And then for our metric of performance, we use intersection over union. So looking at how accurate is this prediction at the end of our simulation. And then the test ends whenever we either run out of budget or we hit some target IOU. So here we see pipe versus MapX on the left side. And on the right side, we see a baseline where this one doesn't use any predictions. It's purely reasoning over how much coverage do you think I'll see in this space, or how much unobserved space do I think I will see. And then the ones on the top are using this pathwise integration, whereas the ones on the bottom are only reasoning about that frontier point and the value of that. And we see two things. One is that in these cases, pipe does perform the best, especially on the larger maps. But we also see that just integrating the path information alone does not necessarily lead to better performance. And we'll see that more clearly in the next results. These are really pushing for these long tail exploration problems where we're trying to get more full coverage of the space. So we compared the amount of time steps it takes to hit 90% IOU, 95% IOU. And then we also looked at the failure rate, meaning that you weren't able to hit that target before you ran out of budget. And so we can see here again that pipe did very well, had 0% failure rate, and had the least amount of time step to hit these percents IOU. And then we can see with these two baselines where we're comparing without the map prediction, that when we compared them, how doing this pathways integration on this more baseline method actually led to much worse results. And you think this is because that any errors that you have in this estimate of information gain, if you have these errors and they're pretty far off, you're going to essentially be accumulating those over time. And that exacerbates that difference or that bias between the two. And so it really emphasizes the need to have something that is fairly accurate as you're estimating this information gain, especially if you're going to be accumulating it over the entire path. So after we completed this work, there was one question that kept going through my mind, which was, how would these methods compare to a human? So how would a human make decisions differently? But also, what would their performance be if we ran these exact same tests? Where would they rank within these lists? And so we wanted to answer this. So we ran a user study where we had the participants' goal be similar to the problems before, where they're trying to explore efficiently with a limited budget and maximize the accuracy of the map prediction on the top. So they select what they think is the next best frontier, which you can see on the bottom, the little orange dots. The robot would explore, gain more information, and then make a new map prediction. And so we did this test on 5 different large indoor maps. And you can see again the user interface on the right. And we had 13 participants in this. One interesting finding was just how challenging this was. We thought this would be easy and more like kind of a video game. It's kind of fun. But we found that people really found this pretty taxing, and it was very challenging to reason over the different choices, what they think will be seen, reason over the predicted map. And we even had to reduce the total number of tests that we did per user so they wouldn't become too fatigued. And so we found a lot of interesting things. First thing we found was that users did perform better than our baseline. In this case, MathX. So on the right, you can see some example paths. So these were 3 different users from the same starting point. And you can see how they explored throughout the space more to the left, with the orange one going more to the left and the right. You can see in this case that MapX did tend to clump itself up a little bit more and didn't perform as well. And then also what we found is that some users did perform just much better than others, that their strategies and heuristics that they use were much more effective than others. And so some of the insights that we found from these, especially the best users, were one, that they did leverage this predicted map, because that was the objective that we were trying to maximize. And they did use it to essentially reason over what is going to be around this corner, will this building end, what is going to be in this room. We found that they would really balance between the exploration by increasing the accuracy of their map, but also exploiting that map to make really good decisions. And then they would reason over both what they think the frontier would see, as well as what is the prediction uncertainty at that space. And then they really did adapt to the map scale. So you could tell that they were trying to understand how big is this map, so then they could then allocate in turn their budget throughout this space to understand, am I going to have to come back? Should I explore this area before I leave it? Or should I continue to go on and explore this space? And so, yeah. So those are three different from the say start. So this led us to the question of, can we create a planner that leverages these insights, especially of our best users? And that was our motivation for creating NAFXRL, which is a reinforcement learning-based planner for indoor exploration. We use these insights in the design of both our observation and action space for this model. And so for this model, we start again with our accumulated observation map. We create these predictions here in the frontier set. And then for our observation space, based on our user insights, we take in all the different map contexts, such as the coverage scores, the prediction scores, the distance to these frontiers, especially the remaining budget. And then we even pass in the entire map itself to give it some of this context to the scale of the space. And then in contrast with many other RL-based exploration methods, we simplify our action space to just be selecting between the frontiers rather than using motion primitives. What this allows us to do is that we can have a fully sparse reward function where we're only giving reward at the end, which is truly what our objective is just to maximize IOU at the end of the episode, rather than having to create a custom, more dense reward function. And so we compared this to some different baselines. These are just a couple of them. So we have mapx.rl on the top left, mapx on the top right. Then we have a version where we don't pass in any predictions on the bottom left, and then you just have a nearest neighbor approach. And this is just a snapshot, essentially, of one of these tests and what it looks like as it's going out through the space. And then you can see the IOUs in this case that NAFXRL did perform the best in this one example. Here's just another example of with all the baselines where we can see that MapXRL did perform the best. And when we compare this to our full data sets with our testing results, we found that MapXRL was the best. And then most importantly, when we compare this to human users, we found that it did perform comparably. So from these works, we've shown that predictive models are an effective tool for evaluating the value of a future action. We found that integrating estimated information data over a trajectory is effective only if that estimate itself is reliable or fairly accurate. We've shown that we can leverage insights from human decision-making and that can make improvements to our planning methods themselves. And this does raise some interesting questions on how we can continue to leverage the insights of human decision-making to improve our planning methods. And are there ways that we can combine the strengths for an even more effective human on-the-loop planner? So now let's take a step back and look at the broader picture again of autonomous robotic data gathering. So we've covered how informative path planning, disturbance-aware planning, and predictive models contribute to improving autonomous data gathering. And together, these approaches really align with my thesis statement that autonomous information gathering can be improved by integrating these long horizon reasoning, enhanced or environment dynamics, and enhanced world belief models. And so with this foundation, we hope we move closer to an autonomous system that can operate effectively in real-world conditions. So finally, let's look at some of these open questions or future directions I see for some of these work. So one thing that I've learned for working across these various projects is that for each one, they tend to essentially create their own like custom or bespoke planner. And it often doesn't generalize well to new informative path planning applications. But for example, let's say we have a drone that we want to go and search around the buildings, let's say, and you would create some path like this. But then if you were to introduce me to a ground robot, does that same planner work well? How much customization does it take in order to enact this? And if you wanted to also maybe switch out the objective function, can you use the same planner in this case? What if you have a different application? Do you have to customize the parameter if you have to hand tune them? All these changes really bring out this question of how can we make informative path planners more generalizable and adapted to many different situations? And one impactful direction that I would see is to create a generalized informative path planning framework that allows for its flexibility, to allow you to easily be able to apply this to new domains and hopefully increase the impact of these methods. On the aspect of world-based modeling, it really is at the core of how we decide what action is beneficial. And it can be extremely challenging to understand what future actions you should take. But most of the time, we tend to use GUIs models that don't truly encode or save that those naturally occurring structures, patterns, and behaviors that we see in real life. For example, if we were to send a robot to go and map the location of a bird moving dynamically, how would you do that? Especially that the drone has limited battery. Where do you send it in order to create as a model for this? And it's going to depend heavily on what you create for that framework of your world-based model. And so we have the question of how can we leverage online observations and repeated deployments for better predictions and planning? Um, and how can we do this to create world belief maps that are more dynamic and also causal to help us to make really informed decisions? One of the other things I really found in my work and working closely with deploying these systems and with users, if we find that these users are often, they're not experts in the autonomous systems, but they are experts in their domain. And it really raises the question to me of how can we increase the efficacy of this human on the loop information gathering? And for me, I think of these three things too. I find really fascinating, which is how can we enable these non-expert users, which are again expert in this domain, but not expert in maybe robotics, how we enable them to interact efficiently and effectively with the system? So is there a way that we can make these systems be able to infer what is the underlying objective of this person and then be able to adapt online to what that is? And then also when this planner is executing this pass, how does it make sure that what it's doing is interpretable back to users to understand that it is following what they desire? And so really this question of like when and how should a user interact with the Pathfinder? So I'd like to take a moment again to thank all the people who made this work possible. My advisor Vasti, this wonderful committee members. I want to acknowledge all of the wonderful lab members who have really been a support, the full fair insights, their discussions, and been a food role in shaking all of this work. And then especially to thank my family and friends who have been a support over all these years. Um, and with that, thank you for your time and happy to take any questions.